Swayam Prabha. Digital India. Educated India.
Okay, so just a small recap, welcome back, and I've got 2-3 more topics to cover here. We'll quickly finish the topologies. I've got multiple slides. If you were interested in network topologies, then we can talk in details about that. We made a class network, we made a multi-tier tree network. Let's talk about a 3D torus. Now, does anyone know what 3D torus? Oh, I'll give you an example. So, the Blue Jean systems, which played against Garry Kasparov, I think, and beat him, and the earlier Blue Jean systems, they were all designed in a network architecture called ND torus. Well, they were 6D torus, so multiple dimension torus topologies. I'll just give you a small example of how that is constructed. So what you have is, the building block is, let me go here. The building block, every square over here is that switching silicon that we talked about. Okay? And this switching silicon has got certain ports which are basically connecting it to its nearest neighbors, like this. If you consider this silicon, it has got some ports going here, some here, some here. So it connects in both X, Y, and Z directions, X, Y directions, okay? So this is a pure 2D torus or a standard, 2D mesh. You bring in another layer, okay, of the same thing and connect it in that Z direction as well, okay? Then it forms 3D torus. So right now, if you look at a 4x4x4 torus, it means it has got 4 switching elements in each of its dimension. And each switching element is directly connected to a compute server. And now it has got 6 pipes connecting it to its nearest neighbors. Okay? So this is one of the switch. It can be a 7-port switch, as small as that, or it can be a 36-port switch in which maybe you connect 12 servers, and then remaining 24 ports you can divide into groups of 4 ports into 6 different groups. And if you connect these 4 parallel ports to the nearest neighbor like this X, Y, Z, and lastly when you fold back the link like this, you will end up in a torus. If you look at a 3D torus, it is nothing but, it looks like this. It looks like this because you have these switching elements completely folded together. Okay? This topology has got a certain characteristic. It has got decent amount of bandwidth between the switches. The characteristics are more related to, it can have very good nearest neighbor communication. So if your application does not, it just communicates to its nearest neighbor. That means the 12 servers which were connected like this, okay, want to communicate to the 12 servers which are nearby, and it has local nearest neighbor communication, then this topology is very nice because you have subsets of nearest neighbor. Every switch has got 6 nearest neighbor. Okay? It will work very nice. If you are solving a problem which requires an all-to-all communication, okay, then this is not very good. Why? Because it has to now go through multiple hops. In a certain size network, we saw in a class topology, you had 2 hops, or 3 hops, sorry. Okay? In this one, the number of hops is equal, the worst case number of hops is equal to the dimension of this. Okay? So now your latency will get added. You'll have switch latency, switch latency, switch latency, and so on and so forth, right? So it depends on what is the use case. Most of the molecular dynamic codes basically talk nearest neighbor. So for those kind of things, for bio-related codes, this topology is very good. But Blue Jean machines were never used to do CFD. Why? Because CFD codes always do, well, they were used, but they were not very optimal for CFD. Why? Because CFD codes have lots of all-to-all communication. They have a lot of exchanges between the domains wherein you are breaking down your CFD runs, And at the same time, there are certain codes which operate in the Fourier domain. If you operate in the Fourier domain, you will do a Fourier transform. Fourier transform involves a matrix transpose, and matrix transpose does all-to-all communication again. So these topologies are not good for that. There are topologies which, there are practical clusters which are made in these, made using these topologies. There are topologies called hypercubes. Hypercube is something in which, for example, the simplest hypercube, a 3D hypercube is nothing but a cube. Okay? You draw a cube, and this is your 3D hypercube. Every vertex is a switch. It is connected to the vertex in a cube form like this. Okay? And every switch contains servers, n number of servers, depending on how many ports are free. How many servers versus how many link, that depends on what is the kind of bisection bandwidth you want in your network. Okay? So when you have a higher order hypercube, what you do is you take another hypercube and connect it like this, what you see in this diagram over here. So you can go to, this is a 5D hypercube. Why? Because every vertex is connecting to 5 of its neighboring cube vertices. Okay? 5D hypercube, again, maximum number of switches it will have is 2 to the power k, where k is 5. Maximum diameter, graph diameter is equal to k. That graph diameter is nothing but the number of switch hops in your network. Okay? So this is again one way of connecting. SGI, you heard of Silicon Graphics, right? SGI, when it made supercomputers, it got acquired by HP a few years back, but SGI systems were all designed around hypercube. They again used silicon from my company, they used silicon from Mellanox, but you can design systems with that silicon in any manner you want. We talked about that Clos architecture, we talked about 3D torus, hypercube. There are many experimental graphs. There is something called a incomplete flat mesh, wherein you connect servers according to some prime number series. Connect switches, sorry, every vertex is again a switch. You connect that vertex to a particular, it's called PDN. If you are interested, if you want to study more on networks, you can refer to these 2 papers. It talks about something called perfect difference sets, in which you get a solution of a difference set, and this thing basically means that particular switch connects to itself, connects to its next neighbor, connects to its 4th neighbor, 14th neighbor, and 16th neighbor. And then the next switch is just like a modulo operation. You just do a +1 to all the destination. When you do it, you get a kind of a spirograph kind of a network. And the good part about this network is it maintains a graph diameter of 2. That means any server to any other server will have only 2 switch hops, no matter how large a system you make. Obviously, the system size is dependent on the radix of the silicon again, but you can make a 30,000 node cluster with only diameter 2. But it's really, really impractical to construct, as you can see. I mean, how do you map it into servers and switches? How do you do these connectivity? Some people have actually made it. Okay? Example, simple, system architecture is take a 36-port switch, connect 12 servers, and use 24 links for connecting to that different set destinations. So, like this, there is something called a dragonfly topology. Dragonfly topology, what it does is, all Cray systems, all current generation and coming generation Cray systems are made using a topology called Dragonfly. Dragonfly is basically a topology in which you define a group of servers connected to a switch, and then you interconnect multiple of these groups in a full mesh. Okay? How does it look like? It looks like this. So let's say you've got one particular switch, and that switch has got, let's say, I have it here, like 24 servers. Now this switch connects to all the other switches. I'm taking example of this switch. So it will connect to all the other switches in that particular group. It's a full mesh connectivity, okay, with one cable. And then there will be some ports left for doing an intergroup connectivity as well. So it's like all connect mesh, and imagine multiple of these circles superimposed on each other with an all connect architecture. So that's a Dragonfly network. What are the shortcomings? What are the advantages? Well, advantages is it has got good connectivity within the group, okay? But if everybody or every server of this switch, for example, wants to talk to every server of this particular switch, they have only one short link. If you have to utilize more bandwidth, you will have to reflect from somewhere else. For example, you take this link, this one, but you should also be able to take this link, or you should also be able to take this link, okay, like that. So it now results in a very complicated routing algorithm. So there's always, I would say, good points and bad points. There are always compromises. I will never say that this is the best and this is the worst. It all depends on your application and use cases. So how does the connectivity affect your application? Now that's a very important question, because all applications, they don't, depending on how your application's communication pattern is, every server does not communicate with every other server. This heat graph basically shows a 64-core CFD run, which is not done in the Fourier domain. It is a standard solver, and it shows which, it's a 64-node run, sorry. So it just says which node talks to which other node. So for example, if you take first line, it says that server 1 talks to all the other servers, server 2 talks to server 1, then talks to server 3, 4, 5, 6, then it talks to some other servers, it doesn't talk to any other, then some more, and so on. Like that, you can see that everybody is not talking to everybody. Okay? So you can actually make a system or wire a system which is completely aligned to what your application is talking. Nobody does that, by the way. Why doesn't anybody do it? Because 99.99% of the system do not run only one application. They will run, many applications, right? It will have all sorts of applications, and their communication pattern will be different. So at the end of the day, the probability that anybody can talk to anybody is pretty high. So you need to have a network which has got a good capability of addressing the communication pattern of every application. Okay? That's where I talked about these topologies, because I want to talk about, forget these examples of Dragonfly, I want to talk about characteristics of network which are important in a supercomputing system. And I will talk about that looking at a standard 3-level Clos network as an example. So you consider every one of these small orange dots as the leaf switch, as the lowest tier switch in which your server is connected. Now this switch connects to a second tier switch, which in turn connects to the red third tier switch. Okay? Now it's got lots of servers, right? Let's say there is, what is the total permutation of communication pattern in this? It's simple. It's equal to the total number of servers multiplied by the total number of servers minus 1, right? 1 can talk to 2, 1 can talk to 3, 4, 5, like that to 4,000. 2 already talked to 1. Now 2 can talk to 3, 2 can talk to 4, and so on till 4,000. So the total number of permutations is really high. Okay? Because of that, even though we made a non-blocking network, as in the total number of ports going downlink is equal to the total number of uplink ports, there are certain communication pattern in which a segment will be shared. Why will it be shared? Because let's say this particular server over here wanted to talk to this one. It will take this route. From this switch, it will maybe go to this one, come down, and so on. Similarly, this server, the gray one, when it wanted to talk to the gray one here, there is a decent probability that it will go here to the switch, and it may take the same particular segment, even though it might have another segment which was free. Why? Because every permutation cannot have the total number of segments is not equal to the total number of permutations. The permutations are quite large. At the end of the day, there has to be some balancing algorithm in routing which will ensure that all the uplinks have equal number of data being carried up. But till the time that happens, there can be segment sharing. And that is where the blocking nature of a network comes into play. And that is where you cannot have a statically routed network. Because if your network is statically routed, every time this permutation is hit, the segment will be doubly shared. Okay? And if you want to actually characterize a network, you can run a simple experiment. Let's say you've got any network. It can be a class, it can be a torus, it can be a hypercube, what all we talked about. Run an experiment wherein if it is a 2000 node cluster, you divide it into random halves of 1000 and 1000. Choose 1000 source, choose 1000 destination. And now run, make a source destination pair. So you'll have 1000 source destination pairs. Okay? Now you run a network ping pong benchmark between each and every pair. Okay? You will get some bandwidth for every pair. Okay? Now, depending on your routing and your topology and your uplinks and so on, so this graph basically shows how many times the path is being shared for how many pair of servers. I did it for 2000 nodes. So if you take a 6 by 5 by 5 torus architecture, this is the graph. What it means is there were 200 source destination pair which shared their segment 5 times. Okay? There were again around 200 which had 6 paths shared 6 times, and so on. The area under this curve is basically nothing but the total number of pairs, right, which is 2000. Now, what is the best network, you tell me? In this graph, can you tell me which network would you consider as a better network? Which of the lines? The rightmost one or the leftmost one? It's pretty easy. Any guesses? Okay, how many of you will go with this one, the sharp graph? How many of you will say that is the best network? Okay, there are a few. How many of you would say that this 6 by 5 by 5 Tori green is the best network? Okay, so the first guys are right. And why? Why? Because in a perfect network, you don't want segment sharing. What is a perfect network? Every pair being able to talk to each other, okay, without getting affected by anybody else. So a delta function at 1 is a perfect network, right? Because everybody got their own path. Doesn't matter who else was communicating, right? So the more, if you have your topology, which has which is when you plot this function, if it is more sharp and like this, it means it has got the best bisection characteristics in a network. The more flattened network means you've got, very distributed, there are many nodes which will experience 4 times oversubscription, many nodes which might even experience 14 times oversubscription. And this is very, very bad for a parallel job, because in a parallel job, it is always the slowest guy which actually defines the outcome. Because unless and until the slowest guy has finished its iteration, the next level of iteration cannot start. Everybody has to exchange their data, right? So you need to have a network which has got very good non-blocking characteristics, and it is like this. It has a peak. As I said, a perfect network can only be a single crossbar switch in which all the servers are connected together, right? A perfect topology can be the one which is only a single crossbar will be a delta function at 1. Any topology will always be a distribution, and the sharper the distribution, the better is the network. Again, these are all from real systems. This is from Oak Ridge National Laboratory, which runs the world's fastest supercomputer right now. And there you run adaptive routing. If you're not running adaptive routing, then this graph basically shows network efficiency. Network efficiency means how many pairs achieved 100% of their design bandwidth. You will see that there are peaks at 50%, then there are peaks at 33% and 25%. What it means is there were, in that particular statically routed network, there were many computers which were sharing a segment 2x, 2 times. There were many computers sharing a segment 3 times and some sharing at 4 times. When you do adaptive routing, that means when you make decision based on how many uplinks are free and distribute your uplink data based on those free ports, then you can achieve near perfect network. But now who makes that decision of doing adaptive routing? That's where the intelligence in the network comes into play. So your switches in high performance network are capable of looking at their buffer utilization. Like every switch has a buffer, right? Every port will have an input buffer and an output buffer. Only when data comes into the input buffer, you will be able to make out its headers and then do a wormhole routing to the destination. Now, every port and its output will have buffer queues happening. When the buffer fills up to a certain level, it's the network element, it's the network chip which decides, okay, now this buffer is getting full, that means I might have congestion over here. So, do I have any output through which I can have an alternate route in which the buffer is less utilized? If you see that there is an output, then you switch some of the flows from this particular full buffer to the slightly empty buffer port. Because in this class architecture, obviously you have so many parallel uplinks, right? To reach this guy, you can do it like this, you can do it like this, you can also do it like this. So there are so many multiple paths available. It's the prerogative of the switching silicon to choose which path to take in real time, make those decisions in that 90 nanoseconds. Because if the chip is making that decision in more than the switching time itself, then there is no point. Then you're adding more latency. Rather, to choose a separate path, you're adding more latency. So you need to do that fast enough with a particular algorithm and use the alternate path. And this is what newer intelligent networks they do. They are not dumb devices which will only forward based on some source destination MAC and IPs. They will forward, they will make a decision based on various other factors inside the network. Okay? With this, I conclude the topologies and network section of the presentation. Let me talk, since we were just completing this class architecture, so I will talk about another important characteristic. So, if you have created a very large data center or very large fabric, there are going to be errors. I think somebody talked to me about errors in the fabric, right? What happens when there is an error in the fabric? Who corrects it? Or, if there is an error, if there is a drop, then there will be corruption because you're doing a DMA operation. There will be memory corruption. So you need to have various mechanisms of making sure that the data that traversed was all good, right? And it is done at various levels. It is done at various layers. One of the layers is doing that on the file layer, doing the 8-bit, 10-bit encoding. So for every 10-bit you transmit, only 8-bit is the actual bit. It is the standard Hamming code encoding. Okay? It is called forward error correction using something like Hamming code. It is called Reed-Solomon FEC. There are multiple FEC mechanisms in which you transmit more data, but the actual data is less. There are some bits which are, so that you can run some algorithm and get back the bits. Okay, that's done on the file. There are CRC checks on the packet level, right? Those are very standard. All that is done on the adapter cards at the endpoints. But what about errors which got injected by maybe a bad link? Let's say server A wants to transmit data to server B. Okay, so this was the route. The data will go to the level 0 switch, it will go to the mid-level switch, it will go to the top level, then it will come down, and it will go to server B. Okay, consider a scenario in which this particular link failed or this particular link had some errors. It's automatically built into the switches that if there was an error, it will find an alternate path. Okay? So when the data goes from this server, it will come to this switch, it will say, that link is bad, I will take the alternate path. Okay? It will reroute. It will come over here. That's fine. Okay? What if one of the downlinks failed? Because in a class architecture, there are multiple ways to go up. But once you have reached the root, okay, there is only a unique path down. Okay, you can see it from the graph. There is only a unique path down. So what happens when one of the downlinks failed? So data will come here. Sorry. So data will come here. It will go up. It will go down. And now it has no way to go. There is no alternate path to this server because this downlink has failed. What will happen? There is a dead end. The packet will get dropped. Okay? Because there's nothing that can be done. The packet will get dropped, that's fine. But then there are mechanisms in the upper layer, in the software, which will say, okay, I was waiting for this particular sequence number of my packet, it never came. It will ask for a retransmission. And that's a killer in supercomputing applications. Why? Because imagine, we were talking about 90 nanoseconds, 10 nanoseconds and all those kind of latencies. When there is a dead end drop like this, there are some software counters which come into picture now. There will be retries happening. The retry will happen for multiple number of times, right? Till the time you have programmed your library. By the way, all these are programmable values inside your library, inside your libverbs library. So there will be a lot of retries, and then it will ask for a retransmission. The latency for this is almost 100x more, or maybe even 1000x more than the standard switching latency. Now your parallel application, because of one simple link failure or one simple flaky link, is completely gone. You will, when I say completely gone, I mean it will finish. But it will finish in a time which will be almost 2x of what it was supposed to finish. And this is a very common scenario. When you're looking at a 5,000, 10,000 node cluster, the probability that one cable might be transmitting some error is a very common phenomena. Even if you take an MTB of 10 raised to, minus 10 raised to 15, if you take a bit error ratio of 10 raised to 12, okay, that is like 1,000 billion bits. Okay? But if you are transmitting at 100 Gbps, okay, within 1 second you will get a bit error, right? So if you have improved your network to 10 raised to minus 15, still in 1000 seconds you will get an error. And if there are 1000 links or 10,000 links or 20,000 links, you will get that error in less than a second. So there is no way to kind of overcome this. This is again pure physics. This is pure manufacturing. This is manufacturing limitations as well. Okay, you can't have perfect hardware. That's where you need to have, again, intelligence in the network. This is what all I'm talking about is the additional things that are present in high-performance networks compared to a standard Ethernet. Now, this switch has capability to talk in any of these switches. I mean, okay, we have implemented, my company implements in this. There are other companies who implement it in another way. What they implement is, the switch is capable to talk to the previous switch, and whenever it sees that there is a error in a downlink or an error in any of the other link, it sends a failure in routing notification packet to the previous switch. It says that my downlink, which carries data worth all these servers, is flaky. Please find an alternate path. This root switch, upon receiving that packet, basically says, okay, right now to reach these servers, don't go through this switch. Please, please go through some other switch. But this one does not have any other link. So it will relay the FRN to this particular guy. Okay? Now this guy will relay it back over here, and this guy has got an alternate path. This relay happens again in those 90 nanoseconds. And this is all done offline. Offline as in it doesn't happen while your application is running, it is running continuously, okay? So when this kind of thing happens, this data is transmitted over here instantly almost. Compared to that milliseconds, it is nanoseconds, okay? And this guy updates its forwarding table so that automatically alternate paths can be taken. And this is one of the very important aspects of a high performance network if you have to use a fabric for a parallel workload. Yeah. It may overload some of the link, correct, but the penalty for that overload is much, much lower. It's actually 1,000 times lower than a packet retransmit penalty. So what you do, your application will still run, it will complete much, much faster than what it would have if there was a dead end drop, okay? At the same time, this switch gives you an alert that something is wrong with my link, come and fix it. So the sysads basically will go and fix it. You know, as an SDN, this is a pure SDN concept. There is no individual routing protocol running on the switch. There is a single routing manager running in a host or in one of the root switches which populates the forwarding table everywhere. And that routing engine also tells you out of band all the failures that have happened in real time. So you can go and correct it. But this mechanism ensures that you have complete, redundancy and no failures when you're operating the large cluster as a single unit. So yeah, this I already drew. So this is what happens, and then data takes a alternate path. So much for some amount of animation. Lastly, so these are the smarts in the network that we are talking about. Let me conclude this part by talking about one more very important. So there is the lines between segregated compute, network, and memory elements is kind of fading away. There are a lot of mixing happening. For example, now we talk about something called in-network computing. Please process the data as it moves. Okay? Don't wait for the data to get into a compute element. The philosophy here is operations, network operations, or even compute operations that are closer to the network should be done in the network rather than run as a C code inside your processing element. And I'll give you an example of one such operation. Okay? So this, again, these are marketing names for how it is implemented. What is done is, before I go there, let me give you an example like this. Okay? We have something called MPI all reduce. What is MPI? MPI is your message passing library. Like you have your sockets for your TCP. For doing cluster computing, you need to pass messages using some library. MPI is that library. It is also supported with CUDA. It is also MPI is basically the base mechanism of data exchange between two servers. If you want to send data from server A to server B using RDMA, you call a function called MPI send. And in that function, you will pass on the buffer pointer and the size of the buffer. And then you will send the data. Okay? Every parallel application will do, for point-to-point communication, MPI send. It will do MPI send receive, it will do MPI read, write. There are many such MPIs, operations. There are another set of MPI operations called collectives. Collectives are operations which basically scatter and gather data and also do reduction on data. Okay? What is gather and scatter data? So every compute element solved its problem, and now it has to send its data to everybody else. Okay, it will do a scatter. Or let's say one master process requires data from everybody else. Okay, so it will try to do a gather. Let's say there is an operation where you need to do reduction in the data. That reduction of data can be basically, okay, everybody give me your output, I will take the average and I will distribute the average to everybody else. Okay? So the reduction operation here was nothing but taking an average, right? How does it happen in a traditional parallel architecture? Well, you'll always have a fabric, you'll have a network there. You will always have a master processee, okay, which will want to gather everybody's data and do that reduction operation. Okay. How will it happen? Well, it will ask for that data from server number 1. The data will flow like this, come over here. Then it will have to ask data from server number 2. Well, it will ask data from everybody in parallel, but it will receive only in serial because there is only one link to that master process, right? So it will get data from every server, one after the other. Only once it has got all the data, it will take the average. Once it has taken the average, it will now distribute to everybody else. So it will follow the same process. Okay? Distribution can be done by using some protocols like you heard of multicast, right? So you can do a multicast. You can do equivalent of a multicast and okay, data gets replicated and in a single cycle it went everywhere. But gather is not a multicast, right? It's an incast scenario where you can only do it one by one. So can you somehow accelerate this process? And the answer is yes, you can. What do? Instead of running the reduction operation as an MPI C code inside your master node, okay, you can run that on every switch. What if I told you that, let's say my switch has got some floating point units which can actually do simple operations like taking this average, doing some reduction. Okay? Now what happens is, when you do a MPI all reduce call, it is distributed to all the switches. And the switch can now in parallel connect data from all the servers which are directly connected to it. Okay? When it does that, because it has got one link from every server, so it will just give one instruction to the servers and say, give me all your data, give me all your resulting data. Okay? It will get the data, it will calculate the average. It's a small, small floating point unit which can just simply take 8 byte, 16 byte, floating point numbers and it will do the average. Every switch can now take that average in parallel, right? This guy doing its average is not dependent on this guy doing its average and so on. Once everyone has done it in parallel, they will distribute the data. The upper level guy will take everybody else's data. One of them will designate itself as the master root. It will take the resulting data from every one of these leaves and do the final average. Okay? So one step, first average is done. Second step, the main average is done. Third step, it is given to the master node. So it's a 3-step process. Whereas earlier, traditionally, if you were running it in a C code, it was a n-step process, where n is equal to your number of servers or number of processes, right? So now, as your cluster size increases, instead of your all reduced latency going exponentially up, you have almost a flat latency. The only step function that you will see here in the latency will be when the network is getting one more level. So if it was a 1-level network, there will be one step here. 2-level network, there will be another latency added because of this level. And then 3-level network, another latency. But this one was geometrically increasing, almost exponentially increasing, whereas this one remains almost flat. So to get better performance, it's not just about the bandwidth and the latencies. It is also about how much of intelligence is there in the network. And this is one of the important things that is added into most of the high performance networks for supercomputers. And if you look at it in terms of real world numbers, just as these are all taken from 60,000, all reduce of 60,000. That means you had 60,000 processes distributed across a cluster. If the cluster was 10,000 nodes, every node, maybe 1,000 nodes, then every node has 60 processes. That means I was running one process per core. okay, and I wanted to do a reduction of all this. If I run it in software, the latencies are almost 200 to 300 microsecond. If the same thing got done inside the network in hardware, the latencies are almost 20 times, 10 times lower. And these latencies add up to your actual runtime of a parallel code. More than running it faster, I'll give you a good example where these things were so important. And this is not a very scientific example, but it is one of the Formula One companies. Most of the Formula One companies, they deploy very large supercomputers for doing CFD analysis of their racing cars' aerodynamic structures. Okay? Ferrari being an example, or Mercedes being an example. Now, as per F1 rules, they get a certain amount of compute time and processing, just so that richer companies don't always win. Every company is allocated only a certain amount of simulation time. Okay? Therefore, these companies want to do as many iterations as possible in that allocated simulation time. So if these kind of technologies bring to them a lower runtime, they'll be able to do more simulations, more iterations, and they'll be able to do more experimentation on which wing setting or which flap setting for their car is good for a particular racetrack, rather than actually running it on the racetrack. So they pay a premium for these kind of capabilities. Where is it important in scientific community? Well, in the scientific community, people want their codes to scale. They want to run bigger and bigger problems, right? For example, if you are trying to simulate a 100 million grid point aircraft, how would it fly? And you want to do a direct numerical simulation for that. It requires a huge size computer. And there, if you have your networks which are not so optimized, no matter how much amount of compute you throw in, your simulation time will not go down. So simulation time goes down to a certain limit, then it flattens out. So basically, you're just wasting electricity, nothing else. So if you want to run a bigger problem, you need to have these smart networks, and you have to reduce these latencies, because every iteration, these latencies actually affect your runtime. So that said, again, okay, one more thing, I'll give you an example. Since we talked about AI and machine learning, I'll give you a simple example of facial recognition, okay, and how a network which does in-network computing can benefit that facial recognition. So how do you do that, recognition? There are always training agents running, there are parameter servers, right? So you will take a base image when you're doing training, and then you will compare it with, again, another particular image. You will calculate delta at every pixel, right? If you have to say whether this particular image is you've got a trained image, you've got an image of a cat, and you want to train your machine to recognize a cat. So you're going to show it lots of animals and also cat. Now, every training agent is going to compare the image of a given cat with all the other images that it's seeing, and it will take a difference. Okay? It will take a difference, and then that difference, based on that difference, it will tune its model. The difference will be given to the parameter server. The parameter server will calculate new weights for it and distribute the weights back to the training agents. Okay? This operation is nothing but very similar to that reduction operation. Instead of this parameter server running again as a code in one of the servers, what if the switch itself was able to do that calculation of that differential weight and then give it back to the training agents? So now you have accelerated your machine learning. Okay? Of course, here the vectors in machine learning are very large. It is not 8-byte, 16-byte average. So you need to have some mechanism of doing megabytes of averaging, or even gigabytes of averaging. Obviously, that cannot be done in a store and forward manner. So it is done in a more, again, sliding window kind of manner. But all these things are completely put into the switching elements, and it accelerates. So when you look at, with using nickel with a tree, ring, and sharp. This is again four node system where we are looking at the bandwidth in Gbps for multiple HCAs. And if you're looking at DGX box based systems where you're looking at all reduced bandwidth in the nickel library of NVIDIA, which the CUDA library, I think you would have gone through that training yesterday, then again these latencies are very much reduced. There are a lot of benchmarks which are out there in the open, in public. MLPerf, Facebook's benchmark for variable autoencoder. By enabling and disabling in-network computing, there's almost 20% of performance boost on the same hardware. So you have a particular hardware, okay? You have the same GPU, same number of servers. You try to do it in a traditional way versus you try to do it by enabling the smarts in the interconnect, you have 20% performance boost. This 20% performance boost relates to almost either 20%, you use 20% lesser system, or you can do 20% more work in the same time frame. Okay? So scaling and going in the exascale domain or multi-petascale domain is fruitful and possible only when you have intelligence in all your elements. I'm only talking about network element because I'm from network domain, but of course all companies are working in all these domains. Somebody mentioned to me about storage. So yes, storage is also one of the most important parts, because when you do iterative process, you do it within the node. Fine, you are already operating within the system RAM, but you would generate a lot of scratch data. That scratch data goes into a high-speed, maybe flash-based drive, which is there in your compute node, which is a /scratch maybe, right? That read-write to your memory should be fast enough. If that scratch was a spinning disk, you will take milliseconds to write to it. Obviously, with the advent of solid-state drives and NVMe over NVMe drives, the latencies for writing into those devices have reduced multi-folds. And when I say multi-folds, I mean 10x to 100x. When the latency of a spinning disk, if you had a normal desktop and if you want to write a block of data into your disk, it is around 10 milliseconds. The same latency on an AND flash is less than 10 microseconds, right? So there's 1,000 times benefit there. There are lots of new advances on the chip side of storage, but then there are a lot of new advances on the protocol side of storage as well. What storage protocol you use when you write on your storage? You use standard NFS, right? Or you use CIFS-based, Windows file share. In parallel computers, you use a parallel file system. You use a file system, you use a parallel file system like Gluster or Luster or GPFS, wherein data coming in is written, it's kind of striped and written in parallel to hundreds of disks. And therefore, you can do very high bandwidth read and write. And all these storage devices also do hardware RDMA, which I talked to you, the basis. So you're doing a DMA on the disk directly now. Memory copy onto the disk. Okay? So all high performance computing systems have, apart from these network things, optimizations on the storage as well. And with this, I will conclude the the high performance network part. And I just want to give you a small whiff of, since you'll be familiar with Ethernet, so just wanted to we talked about a lot of differences between high performance network and Ethernet, but there are a lot of convergence happening on Ethernet as well. So InfiniBand or Ethernet or any proprietary fabric, what do you want to use in your cluster? Maybe you're setting up a GPU cluster, whether you want to connect it over standard Ethernet, because Ethernet is also available in 100 Gbps, right? There is a 25 Gbps, 10 Gbps, 100 Gbps Ethernet as well. What is the difference? Well, first of all, traditionally, most of the Ethernet networks are designed in a core aggregation leaf kind of architecture or core aggregation TOR kind of architecture. Many times, the lower level switches are pretty dumb. They are just forwarding guys. And the actual switching happens only in a core. Okay? So this is a pure campus network. If you look at your institute's network, all your hostels will be aggregating to a particular box in the hostel wing. The wings will be aggregating to one particular switch. That switch will be connected to your core switch, which is in the computer science department somewhere, or your data center somewhere. So those networks are pure standard campus network. But you can also make a leaf spine network with Ethernet. What is stopping you in making that? A high performance, non-blocking leaf spine network using Ethernet switches. You've got 36 port 100G Ethernet switch. One challenge that is there in Ethernet is there are lots and lots of protocols that need to run. Okay, when you have to have a leaf spine architecture with multiple servers connected to multiple switch, now you need to run something called, you need to do channel bonding. If you have to do load sharing between multiple parallel uplinks, what do? You do channel bonding, you do LACP, right? With LACP, you distribute the data into multiple uplinks. Then how this is routed, you cannot run a pure L2 network, very large. You can run a L2 network, pure L2 network of a certain size, but let's say if you go beyond 1,000 nodes, or maybe even 400, 500, 200, 300 nodes, if you bring in another server, there will be an ARP storm, right? The server will say, I'm present, and now it will start relaying its ARP to everybody else. There will be an ARP storm on the switch. Nobody can be able to stop it. Okay? So you cannot have a pure L2 network. So now you need to run something called layer 3. Okay? When you have protocols like OSPF or BGP, BGP, Border Gateway Protocol, that runs over the entire internet. So you need to have different kind of protocols to make sure that that fabric is running. That's where there is, some amount of, I would say, complications in an Ethernet. But it still can be done, and it is done. Okay? LACP is Link Aggregation Control Protocol. It basically says that if I have multiple uplinks available, let's say from one switch to second switch, I connect 4 cables. Okay? Data will go through only one of the cables. More data coming in, again, it needs to go through some of the cables. So what is the protocol that balances the data so that all the links are utilized? That protocol is basically, the bonding protocol, LACP, multiple modes. How does it balance? Basically, the protocol, the switch, looks at the packet headers. Okay? It runs a hash function. So you run a hash function wherein all the flows coming in, the switch will look at its packet headers, and it will calculate a hash based on the headers, because every packet will have a different source, destination, MAC or IP, right? So it will say, okay, if the output of my hash function, which is operating on this MAC or source IP, is A, send it to link 1. If it is B, send it to link 2, so on. So it will be able to balance amongst multiple links. So there has to be a protocol that is running on each and every switch in Ethernet, which kind of makes sure that every link is load balanced properly and utilized. So these are the complications that you need to do in an Ethernet fabric. You have to configure all that to make a parallel workload run on an Ethernet fabric. So, exactly, but there is a centralized routing entity called subnet manager. It's an SDN concept. Okay? So rather than every switch running its own protocol and defining its load balancing, there is a global load balancing which is kind of defined. And that's where that adaptive routing comes into picture when I told you, right? So every switch automatically, without any protocol, in hardware is able to route based on its buffer utilization. It's able to route on a free link. Okay, so there is no, LACP is a C program. It is a control plane protocol that runs on top of the data plane. See, every switch is 2 processors. There is a data plane network processor. On top of it is a control plane processor, which is nothing but an x86. It runs a C code. So LACP is actually something which runs in the control plane, and then it is programmed in the switch. The hash functions and everything is programmed. So all that takes time. In adaptive routing, it is the data plane itself which is taking all these decisions. So it is much, much, much faster overall. Okay? So apart from, rather than going into the details of how to make a Ethernet fabric for HPC, I will just talk about RDMA, because we established that as a base technology requirement for high performance computing. There is now capability of running RDMA over Ethernet fabric as well. Why? Because RDMA at the end of the day is the capability of the adapter cards, because it is the adapter which is doing the DMA operation. The fabric is just a conduit of sending the data, right? It's just a conduit. What you need is, if you are going to have a fabric which is going to do DMA, then you need certain characteristics. So first of all, how DMA is done, if you look at an InfiniBand packet, it is basically just this part. InfiniBand packet consists of a global routing header, something called a LRH, a local routing header, then something called a base transport header, which contains the pointer to the remote system's memory location where you want to do DMA and the length of your DMA operation, and then just the payload. Payload is your actual data which will be DMA'd onto the destination. And of course, there are some invariant cyclic redundancy checks and frame check sequences and all that. Okay? InfiniBand switches, adapters receive this. The switch basically operates on this area and then decides where the packet has to go. Once the packet has reached the destination server, the NIC card, the InfiniBand NIC card, basically looks at this header and sees, okay, where the DMA has to be done, and then it does a DMA of this payload to the system memory directly. What if I encapsulate this, okay, entire data, entire this InfiniBand frame as a payload of an Ethernet frame? I can very well do that, right? And that's what is done in running RDMA over Ethernet. So now I have a standard Ethernet frame which has got the Ethernet layer 2 header, it has got the ether type, and it has got the IP header and port number and so on, and also the UDP header. So RDMA on Ethernet is always transported as a standard UDP packet. Inside the UDP packet, the port number, the UDP port number, basically it is reserved for saying that this particular packet is an RDMA packet. Please treat it in an RDMA way. If the network card is not capable of doing RDMA, it will just treat it as a standard Ethernet frame. But if it is capable of doing RDMA, the network card will look inside. For the Ethernet frame, this entire thing is the payload. Okay? So the network card is going to look inside the payload and look into the transport header. And if it sees that this transport header had the DMA operation commands, the DMA memory pointer, and the DMA block size, it will put this payload into the system memory. So that means pure RDMA can be done on standard Ethernet fabric as well. And you will be surprised to know that 80% of the machine learning clusters are actually built over Ethernet fabric. Can anyone guess what's the reason? It's pretty simple. The reason is their network administrators are not from HPC background, so they're only familiar with Ethernet fabric. Okay? And no company basically wants to invest in getting academics who will run an InfiniBand or a proprietary high performance fabric. So they want every of these functionalities capable of running on Ethernet as well. So they run on Ethernet, and we bring all these companies, they bring these technologies on standard Ethernet. So we basically Mellanox was one of the founders of RDMA, and we put it in the standard IEEE as well. So RDMA over converged Ethernet is now a fully standards-based protocol, part of IEEE, I think. And also, you won't, so one more new thing is that NVMe drives, if you want to export over a fabric, runs over RDMA. So there is a protocol, like there is protocols are TCP protocol, there's a fiber channel, right? Fiber channel is a protocol for high performance storage. Similarly, NVMe over Fabrics is a high performance protocol for all solid state drives that you want to share over the network. That's also an RDMA. So basically, RDMA can work on Ethernet. You do need some neat functionalities or features from the switches. And I think I'll just talk about one of those features, and then we can close and maybe do some question answers as well. One is the buffer architecture of your silicon should be fully shared. What it means is, generally what happens, so when people started designing Ethernet switches, you started increasing the number of ports. Now it's very easy to design a tiled architecture where you will design a tile of 8 ports and then you will replicate those tiles in silicon and create a single package out of it, right? There will be minimal interaction or no interaction between the multiple tiles, but there will be still a common forwarding table which will make sure that if data is coming on this tile and wants to go over that tile, it can be routed. But this kind of architecture presents a very big bottleneck in HPC systems. 90% or almost all of the Ethernet silicon designed today are with tiled architecture. Silicon which are designed by Cisco networks, silicon which are designed by Broadcom, which is the largest manufacturer of Ethernet silicon. They all do this tiled architecture because it is easy to implement. Okay? But when you have HPC workload and you have many to one kind of scenario, okay, all these ports will be able to queue into only 1/4 of the total available buffer. And let's say you have a scenario in which there are a 4th server comes in and wants to talk to this, but the 4th server is connected to this particular port, then these 3 ports will share 1/4 of the buffer, and this guy will get full 1/4 of the buffer. So when you run bandwidth many to one between these computes, this guy will get much higher share of bandwidth. If all of them were transmitting at 100 Gbps, this guy will get 50 Gbps, and all these guys will get 16.66 and so on. This is not at all conducive in a high performance computing environment. So you need a fully shared buffer architecture where no matter which port you are connecting your source and destination, you should not have any fairness issue inside your switching fabric. Now these are pure characteristics of the ASICs which are used to make the network processors. Okay? Similarly, again, this was actually highlighted by Facebook. So by the way, most of these, the Googles and the Facebooks, they run the largest data centers, much larger than the biggest HPC system out there. Like one data center in a Facebook, it would be 200,000 servers. Not 10,000, not 20,000, 200,000 servers. The only difference is they don't run a parallel job. Okay, they don't run a MPI job, they don't run a scientific parallel workload. So they're not termed as supercomputers, but they do have very large networks. And they are the ones which are affected by these, unfair buffer issues inside their networks. Because of these issues, even if they're trying to load distribute amongst a lot of their servers, they are not able to because certain servers are getting more load and certain servers are not getting more load. I'll give you a simple example. Look at a payment processing company like Paytm or a PhonePe, wherein everybody is hitting their data center. Everybody is doing some transaction, and now PhonePe.com is a single. It's like an Anycast IP. So everybody will end up to a particular IP, but now there will be multiple servers servicing this Anycast IP, right? So that multiple servers can do load distribution. If their fabric is not fair, then even though they have made a complete symmetric fabric, some servers will get more load and some servers will not get more load, right? The load distribution in these kind of networks are not done using load balancers or firewall. It is actually done by the fabric itself, because you don't want certain servers to be a load balancer where all the internet traffic will hit, and then those load balancer will distribute the data to applications on multiple parallel servers. Actually, the fabric itself does load distribution. Okay? So in these kind of scenarios, this fair buffer allocation is a very important thing. And lastly, I will conclude with this. The important thing is congestion control. If you have many to one scenario, okay, if you have many to one scenario in InfiniBand, you don't have a problem because it is a credit-based network, wherein everybody will get their path and the data transfer will happen only when they have gotten the path. In Ethernet, you will blindly send the packet, and if the switch sees that it is the output is congested, it will drop the packet, right? So now you need to work out some mechanism where the packet is not dropped. One of the mechanism is to send pause frames back to the sender. So initially, almost like tens of years ago, companies came up with, IEEE came up with a standard of sending pause frame. So if the switch silicon detected congestion at an output, it basically sent pause frames to all the senders. And the senders on receiving the pause frame will basically throttle down their packet injection rate. As soon as the congestion is gone, they will start injecting again. But this is a bad thing. Why? Because pause frame is sent irrespective of wherever the congestion is. So pause frames pause everybody's communication. So that's not a solution, because in a multi-tier architecture, let's say if the congestion was over here and this guy sent a pause frame, this pause frame will be reflected to the previous guy. At the same time, it will be reflected to all these guys as well. So even though the congestion was from all these orange guys to this orange guy, even this blue guy is affected, right? Whereas his inlet and outlet port has nothing to do with congestion. So pause is not a good example, a good remedy for solving the congestion problem. Okay. So again, we already talked about it. Why congestion is needed? Many to one communication, hits the switch, and then obviously 2 gets dropped, 1 goes through. So what is needed is, you come here, and now you do only 33% of the bandwidth, right? You try to throttle using pause. Okay. Then they came up with priority-based flow control. That means now you don't do a global pause, you do flow control mechanism. It's a link layer protocol. It is switch to a neighboring switch or NIC to a switch. When buffer fills up, okay, when there is congestion, the buffer is going to fill up. Then the receiver sends a pause frame to the sender. And when buffer empties, the receiver sends the unpaused frame to the sender. So now pausing granularity is based on per priority. So you can have multiple priorities and you can have multiple flows mapped into that priority. So now if you have everybody on the same priority, it is equivalent to global pause. But if you have some flows which are of higher priority, then you don't you will not send pause to those, or you will send less pause frames to those. So priority-based flow control was sending pause frames in a prioritized manner. The better thing to do is, again, this is some animation, that's fine. Let's go. Now, the better thing to do, this also caused some amount of congestion spreading. I will not go into that details. Let me talk about what is one of the best ways of doing this congestion control. And this is actually based on a field in the Ethernet packet called ECN, Explicit Congestion Notification. Okay? So what happens is, when there is a congestion in the fabric, at any point in the fabric, you set up an ECN bit. There are 2 bits there. Instead of 00, you set it up as 11, okay? And then send the packet forward. Now, here, let's say there a communication is, you have a sender NIC and a receive NIC, and you have the switch. Now, switch is your congestion point. So the switch is the one which is going to mark if it is congested, it will mark the packet with ECN bit. Now this ECN marked packet goes to your notification point, that is your destination. So on the notification point, when it receives a packet with congestion marked bit, it sends a congestion notification packet back to the sender. Okay? And now the sender, upon receipt of this congestion notification packet, can start throttling down its packet injection rate. So this is a full, pure, closed loop, closed control loop, like we did PID controllers, right? So it's a full control loop which is a closed loop, and only thing that is required from a Ethernet switch is the capability of detecting the congestion, marking the congestion bit, and then the endpoint adapters at both the sides will take care of making sure that congestion is not there. How does it make sure? By the way, this is much faster than implementation in software because it's all done in hardware. As soon as, when is a congestion bit marked? Okay, packet has come in inside the switch buffer. The buffer is getting a bit full. Okay, I set up a watermark in that switch buffer. I say, if the buffer is utilized 80%, please mark ECN bit. Okay, and then send it forward. On reception of the ECN bit, CNP will be sent back. The sender will throttle down. The sender will throttle down so that the buffer utilization now goes below 80%. And now the ECN bits will not be marked. Okay? Of course, we don't do just on and off of ECN bit marking. There's a very complex algorithm of when and what amount of packets to mark with ECN bit, when to increase the probability of those marking, and so on and so forth. So, and these are the IPs and the patents that companies have basically. But in practicality, this is the mechanism. Okay? And this mechanism ensures that even in a large fabric where there can be a lot of congestion elements in the fabric, you will not have packet drops. Okay? This is what we call lossless Ethernet fabric because of end-to-end congestion management. How would you do the rate change and all? This is what I'm talking about. And then comes a very important question. What if, because of congestion, my CNP, my congestion notification packet, what if that itself gets blocked? Right? So, because it's also sharing, physically it's sharing the same port, it's sharing the same buffers, right? That's where you need to have capability inside the switch where you mark multiple buffer pools. You say that in my switch, and again, it is all has to be done in hardware. So this is all hardware architecture of your switching silicon. So now you have multiple buffer pools, and you say CNPs which are coming are characterized by a certain format. CNPs should be sent into a buffer pool which is not using a weighted round robin, or it is using a strict priority of 1. Like, please pass that across no matter what. Okay? So when that kind of switches are used in the fabric, then obviously there is full end-to-end congestion notification. There are various, there are tons and tons of mechanisms on how this buffer management, how the congestion, I would say how the balancing between elephant flows and mice flows are done, because there are many times CNPs are very small packets. If it gets stuck in between very large streaming packets of your application, then again it will not go to the destination or to the source on time for the source to throttle down, and source will keep injecting and there will be drops. So all these mechanisms help in creating a lossless network. So you have a big AI ML platform with a lossless fabric. So just give you some example. Just look at a test setup. You have a small cluster is nothing but everything connected to one switch, and I'm saying large cluster is one with multiple switches in between, and then you run throughput, throughput per sender. Then there will be some pause, and then what would be the throughput distribution in this? Let's say if you are doing a very high load and you have no amount of congestion management, then throughput of every sender looks somewhat like this, because randomly everybody is getting packet drops, right? So depending on which sender receive pair got packet drops when, over a period of time your throughput will look something like this. There is no way you can run a parallel application when your communicating pair have that kind of throughput. When you have this ECN based lossless fabric congestion management done, then your throughput looks something like this. Okay? So if you do it over standard TCP without any congestion management, this is what it is. When you do it over RDMA with congestion management, this is what you get. So at the end of the day, these technologies, all these things that I talked about, are impervious to getting good performance or even good functionality out of an HPC systems. And just to leave you with this last thing, so the next generation of HPC or even networks for large data centers are actually SoCs. This is the architecture of one of our latest network processor. It's actually a system on chip which has multiple ARM cores. It has got all those RDMA blocks. It has got inline IPsec TLS encryption decryption. So I mentioned, right, the philosophy is network operations should be done closer to the network. When you're doing encryption decryption, it is actually, you want to encrypt data on the fly. Why do you want to run that encryption decryption algorithm as a C code again inside your server? You will be utilizing your cores. You will be much slower because every data packet has now to go through that encryption code, encryption subroutine. So we implement IPsec or TLS encryption in hardware with state machines. Key management is done between the there's an SSH establishment between the two endpoints in the network itself. So it's like a bump in the wire. There is a lot of programmability in the network because now you can offload rather, apart from offloading just few of the things as I gave an example, the example that I gave, you can offload many other network functions on it. So next generation systems which we are designing and developing, which not just we, the whole industry is developing, is smart interconnect with programmable interconnect. These are what are called smart NICs. Okay, smart and programmable NICs, C programmable NICs. These are the ultimate, it's like a co-processor. That's why I'm saying it can be used for many things. In a cloud environment, if you want to do bare metal provisioning, or if you're running containers, you're running HPC over containers or over virtual machines, and you want to access your adapters over SRIOV, like without any software virtual interface penalties, then these are the adapters which are there. Just to conclude, as I said, I'll reiterate, boundaries and distinction between pure compute network and storage is fading, and intelligent networks and processing data on the move is the right way to take us to exascale and beyond. And with that, I will conclude my presentation. I think we have 10 minutes to talk. Sure.
So are we not just increasing the area of the switches by adding more hardware, like hardware or security hardware that you talked about?
Sorry, yeah, so about these you're saying?
So we are just adding hardware.
Yeah.
So we are just increasing the area of these switches.
Exactly, we are. So that, we are not actually increasing the area of the switches because there's a very nice balance here. As the process technologies are shrinking, so if you look at a standard, x86 processor, now it has billions of transistors, right? Because it has got so much compute elements and so much of cores. Switching system, on the other hand, is not area limited by silicon because of the logic inside. Because switching is pretty simple, it doesn't require so many gates to do the switching. You need actually more area for the switching silicon because of the first principles thing which I talked about, the phi. Like if you have to take 40 ports out, you have to take so many pins out. A switching silicon, right now our current generation silicon has got a 3600 pin on it, okay, it's much more than a processor. Why? Because you need those many pins out for actually driving. Now you cannot take those many pins out from this smaller silicon. You need a bigger die. I've got much more space on the die actually, right? So I can do more compute and memory on the die just because I'm pin limited. I'm constrained by the size because of the pins that I'm driving out. Okay? So in effect, we are not, as a company, none of the commercial companies increases the die size beyond the practical limit because it reduces the yield. When it reduces the yield, it reduces the money that we make. So finally, everything is driven with money. So, you always optimize. You always optimize and see in what dies, what all features can you put in. and then you keep on adding features. When the process technology shrinks further, you can actually put in more logic inside the elements. Okay? Similarly, in the networking elements, the IPsec and all that I talked about, it is part of the NIC. If you take a very basic NIC, it is nothing but a conduit between a Ethernet to PCI Express. All it does is protocol conversion from a Ethernet frame to a PCI frame. Everything else is done by the CPU. Okay? But that thing does not scale, because as I said, if you are not doing any intelligence in the network, you need to have that intelligence somewhere. That intelligence now has to run as a C code in one of your cores. Now doing that is a much slower process, because all the data will go inside some buffer, and then some subroutine will read that data, operate on it, and then give it to the application. If it was done as a bump on the wire in the fly on the network, it is n times faster. So it is much more beneficial. It's driven by obviously technology as well, and also demand. There are a lot of people who have that performance demand that they. So we sit with all these users, the Alibaba, Tencent, Baidu's, and Google's, and Facebook's of the world, and every 6 months we sit there with them and they say, okay, now to address a certain problem, we need these features, and we have to implement or put those features in hardware in the silicon, and that's how we define our roadmap. And similarly, we also define the roadmap with feedback from various research institutes who deploy those large clusters that I talked about in the beginning, and keep on adding these functionalities into the systems. So yeah. On-chip network, okay, so there are a lot of talks of optical networks, photonics-based networks, and so on. We work with a lot of photonics, a lot of silicon photonics, but right now, practically, we still feel that having optical switching complete. Right now, we are doing electrical switching, right? The switching is happening completely. Optical switching is when, for example, you can take some MEMS-based mirrors and reflect light between the source and destination inside a silicon. Or, any photonics-based switching where you have, structures inside your silicon which will be modulated and which can do optical switching. So those kind of things, we are not, it's all in R&D. There are a lot of people who are working on it, but practical systems based on that are still some time away. So we are still into standard, 14 nanometer, 10 nanometer, 7 nanometer process to have faster and faster switching. By the way, we go to, as a network company, we go to a lower process, like a faster process, not because we want to cram in more transistors. We have to go to a faster process because we have to switch faster. By switch, I mean not packet switching, but the analog signal switching has to be faster, right? So you have to have a faster transistor for that, so lower process. Anyone else? Or we're good? So yeah, if you have any more questions, I think my contact details and everything will be shared along with the ACM, minutes and briefs. You can reach out to me anytime and we can talk. Great, so thanks. I think thanks for your time, and we'll close here.